Ever glance at your speedometer and think, how do we even know that's how fast I'm going?
Good question.
Get ready to unpack the physics of motion and time, because today's deep dive is all about the fundamentals we experience every day, but rarely stop to question.
And our trusty guide on this journey,
Don't tell me.
a ninth-grade science textbook.
Oh, perfect.
Don't underestimate it, though. Sometimes revisiting the basics can spark some seriously interesting insights.
Absolutely. It's like that saying, the more you know, the more you realize you don't know. We're tackling speed, time, even the surprisingly regular world of pendulums, all hiding in plain sight.
It reminds me of how we often take for granted the incredible precision of modern technology. For instance, did you know that GPS technology, the very system that guides us effortlessly through traffic, relies heavily on the mind-boggling accuracy of atomic clocks?
Wow, no, I didn't know that.
Yeah,
That's a fantastic point. We're talking about clocks that are so precise they wouldn't lose or gain a single second, even if they ran for millions of years. It's mind-blowing to think that something so complex is involved in something we use every day. But let's rewind a bit. Our textbook starts with a simple question. What does it even mean for something to be in motion, to be fast or slow?
right. They use the example of a bus and say you on a bike, starting at the same point.
Okay.
It's clear that after 5 minutes, the bus will have traveled much farther.
Right.
But the key takeaway here is that speed isn't just about how quickly something is moving at any given moment. It's about the relationship between the distance traveled and the time it takes to cover that distance.
It's not just about how fast your bike can go, it's about how far you actually travel over a specific time.
Exactly.
Speaking of time, it's amazing how many ways we've devised to measure it, from ancient sundials to those atomic clocks we were just talking about.
It's a fascinating evolution. We've gone from observing the grand, predictable cycles of the cosmos to needing to measure time in fractions of a second, so minuscule they make a nanosecond feel like a millennium.
Wow.
And it's this ability to divide time into infinitesimal slivers that underpins so much of modern technology.
High-speed photography, computer processing these advancements are only possible because we've figured out how to track those incredibly tiny units of time.
Precisely. Think about capturing a hummingbird's wings in flight, or analyzing the data from a particle accelerator experiment. Without the ability to isolate those fleeting moments, those events would remain a blur.
And it's not just about capturing those fleeting moments, is it? Our textbook then dives into the surprisingly consistent world of pendulums and how this seemingly simple phenomenon revolutionized timekeeping.
It's a classic example of a profound discovery emerging from a simple observation. The story goes that Galileo, while observing a swinging lamp in a cathedral, noticed something peculiar. Instead of the arc of the swing getting smaller and smaller, the time it took for each swing seemed to remain constant.
Right, the time period, as it's called, stayed consistent. And that realization paved the way for the pendulum clock. Who knew that the key to accurate timekeeping could be found in the gentle sway of a hanging weight?
It's a testament to the elegance of physics. But moving from the rhythm of pendulums to something seemingly more abstract, our textbook then introduces the power of graphs, specifically distance-time graphs.
Okay.
They might seem like something you'd only encounter in a classroom, but they're actually incredible tools for visualizing and understanding motion.
We see graphs everywhere, but I'll admit I don't always grasp what they're truly telling me. What makes distance-time graphs so powerful when we're talking about motion?
Imagine this. You can plot the journey of anything, whether it's a car, a runner, or even that swinging pendulum on a graph.
Okay.
By plotting distance on one axis and time on the other, we create a visual representation of motion that's far more insightful than simply looking at raw numbers.
So instead of just seeing that a car traveled 10 miles in 30 minutes, we can actually see the nuances of that journey unfold.
Exactly. A straight line on a distance-time graph tells us that the object is moving at a constant speed. But what's even more revealing is what happens when the line curves or bends.
Because a straight line means steady speed. I'm guessing those curves indicate changes in speed.
You got it. A steepening curve means the object is accelerating, covering more distance in the same amount of time. A plateau indicates a period of rest where no distance is being covered. And a downward slope shows us deceleration or slowing down.
That's incredibly helpful. Suddenly, we're not just reading numbers on a page, we're seeing the story of motion unfold visually. And speaking of stories, our textbook brings back our old friend the bus this time with a real-world scenario, a picnic outing.
Sounds fun.
They provide a table of data tracking the bus's distance at different times throughout the trip and challenge us to, well, basically become physics detectives.
It's a great way to put our newfound knowledge into practice. By plotting the data points from the table onto a distance-time graph, we can start to unravel the mysteries of the bus's journey.
And I love that they actually walk us through this process in the textbook. They even include a helpful diagram, figure 9.14, which I have to say was my aha moment. Seeing those data points transform from a table into a visual representation of the bus's journey, well, it clicked for me.
And that's the beauty of it. The graph allows us to glean insights that weren't immediately obvious from just looking at the table of data. We can see, for example, where the bus might have made a pit stop, where it hit traffic, or even if it took a detour. It's all there in the shape of the line.
It's like the graph gives us this secret decoder ring for motion.
Exactly. And that's what makes physics so fascinating. It's not just about abstract formulas and equations. It's about understanding the fundamental principles that govern how the universe works, from the smallest particles to the grand movements of planets.
It's about finding those hidden connections, those aha moments that make you see the world in a whole new light.
Yeah. We started this deep dive with a simple question about speed, and we've explored everything from the precision of atomic clocks to the elegant swing of a pendulum to the power of graphs to unlock the secrets of motion.
It's been quite a journey. And it just goes to show that there's always more to discover, more to learn, and more to question about the world around us.
Absolutely. So next time you're stuck in traffic, instead of feeling frustrated, maybe take a moment to appreciate the physics at play.
Yeah, just think about the relationship between distance, time, and all those other cars around you. Imagine plotting it all on a distance-time graph. You might even discover some interesting patterns.
And just like that, you've turned your commute into a physics thought experiment. What could be more fun than that? Thanks for joining us on this deep dive into the fascinating world of motion and time. Keep those curiosity gears turning, and we'll catch you in the next episode.